So today we're going to cover, so in last lecture we introduced entropy. We talked quite a bit about its consequences, maybe mostly in broad terms and in historic terms of conversion of heat to work, which is an enormous practical consequence. Today we're going to talk more about, specifically about entropy of materials as systems, and then show you what the integration of the first and the second law leads to. Also practically, solutions to problem set should be online. You should be making your way well through the first problem set by now, and some of the readings. And also remember at 1:15 to 2 I have office hours. You're welcome to join to, if you have any questions about thermo, or if you just want to say hello and chit chat, that's good too. And we use the same link as the class link. So any questions about anything from last time? Okay, and as I said many times, feel free if you have questions that come up during the lecture. You can either interrupt me, you're also welcome to type them in the chat window, and then either the GSIs will just respond to them in the chat window if it's an easy thing, or they will alert me. So again, so today I want to start by talking about the entropy of materials. And we'll do that in a few parts. The easy part is actually understanding the temperature dependence of entropy. For a material, because it will lead us to a practical definition of the heat capacity. So if I write down what the differential of entropy is, this is del Q reversible divided by T, but I'm going to put the T here. So TdS is del Q reversible. And this we have learned to calculate under constraints. Right, so we know that the heat flow is path dependent. So this is some path. And this would be equal to C for that path dt. Right, which means that this differential would be valid only under that path. But what you see now is that I can define the heat capacity from the entropy. I can divide by dt here. And so what you find is that T ds dt, right, because this is the ratio of two differentials under the same constraint, so that's a partial derivative. So this under some constraint or along a path is the heat capacity along that path. And the reason that this is important is because, you know, before we could only define heat capacity, which obviously is a property of materials, through a path-dependent function, but now it's actually defined as a property through the properties of the material, which is the way you want it, right, and the way it should be. So specifically, for example, if you have a simple system with only PV work, you could now define Cp as T ds dt at constant P, and Cv as T ds dt at constant V. And any other heat capacity that we talked about before, like if you have more work terms, remember if you have more work terms, then you have more variables, so your dimensionality is higher. So to specify a path, you need more constraints, right? So, you know, if we had a magnetic system, we could have Cp under constant magnetization, and then we would take the derivative of the entropy under constant magnetization. Okay. So this turns out is actually the formal definition of heat capacity. While we defined it, because we didn't have the entropy before as heat through heat flow, the way that formally heat capacity is defined in thermodynamics is as a derivative of the entropy. Also note the units, right? entropy has the same units as heat capacity, right? It's joule per mole per Kelvin, and that works out, right? Because this T units cancel with these T units. Okay. You can look at the heat capacity as a function of temperature. Sorry, the entropy as a function of temperature in the same way that we plotted the enthalpy, and I'll talk later about the reference state, so let's not worry about the reference state. So again, you would have, let's say you're in a solid phase. At some point you hit the melting point. So the slope here now would be, Cp over T, if you did this at constant temperature, right, of the solid. Then you would put in the heat of melting, and so you would have a change in entropy, a delta S of melting, which would be equal to delta H of melting divided by T of melting. You know what? I've drawn the slope wrong here. Not the slope, I've drawn the curvature wrong. This is typically more concave. And then this continues in the liquid, and you would have Cp liquid divided by T, right? There's a subtle point here that I want to point out. Let me actually go to the next board, see if you can. So in general, at a phase transformation, delta S of the transformation is delta H of the transformation divided by T of the transformation, right? Because S is del Q over T, so when I integrate that over the full transformation, the temperature stays constant during the transformation, for example, melting or boiling, so I get delta S and delta H divided by T. This is only true when you perform. So at the equilibrium conditions of the transformation. Right? Because the reason for that was only in equilibrium do we have that ds is del Q over T, right? So because of this, you can only integrate this along a reversible path, which is the equilibrium path. So if I do, say, undercooling of a liquid, if I take a liquid and I undercool it below its melting point, let's say I take water and I solidify it at -10 Celsius by undercooling it, and I measure the latent heat, the entropy of that transformation will not be the latent heat divided by 263 Kelvin, right? Because I'm not doing a reversible path there. In the problem set, there's a problem where you have to think about how you get the entropy of melting under these conditions of non-equilibrium. And as always, the solution is that you find a reversible path between the two states. So if I need the entropy change between, say, a liquid at, let's take water, right, at -10 Celsius, and the solid at -10 Celsius. So I have two states here. How do I find an equilibrium path? Well, I heat this back up to 0, which is the equilibrium temperature. I transform it at 0, and I cool this down to 0, to -10, right? So now you have equilibrium melting here, so you can calculate the transition and be there. And if you follow this path, since entropy is a state function, this difference, right, should be path independent. So the problem with entropy is that you can only really calculate it along a reversible path, right? Which is not true for a lot of other functions we use. And there's a problem like that in the problem set. If you remember the empirical rules we gave last time, the sort of approximate rules, for simple solids, so I typically mean things like monoatomic solids, that was Trouton's and Richard's rule. For melting, for example, it said that delta H of melting is approximately 9 times Tm. So what you really now see is that that's a statement about the entropy of melting, right? Because what that means is that the entropy of melting, which is delta H divided by T, is approximately 9 joules per mole per Kelvin. Which is sort of a remarkable statement, right? It sort of says that for simple solids, they kind of all behave the same when it comes to entropy. And the reason is, as we'll see later when we do statistical mechanics, is entropy is essentially about degrees of freedom. It has no energy scale, and it's simply counting the fact that a liquid spans a broader phase space than a solid. You know, in a solid, the atoms are constrained, they vibrate around their position. In a liquid, they can take a lot more excursions. And that's almost independent of chemistry. Whether I melt copper or whether I melt aluminum, that gaining of degrees of freedom is largely independent of chemistry. The chemistry tells me at what temperature it occurs, right? If you have stronger bonding, the melting will occur at a higher temperature, but the gaining of degrees of freedom is largely independent of it. And if you use Richard's rule, I forget which one is Richard and Trouton, but if you go boiling, so for boiling, we had that delta H of boiling is approximately 90 times Tm. So that's a statement that the enthalpy of boiling, or evaporation, if you'd like to call it that, is about 90. Again, sort of true, I mean true, is an approximation for a monoatomic, for simple solids, basically, right? Okay. So the only thing left is to understand, is to set reference states for entropy. So we did that for enthalpy. And for enthalpy, we chose reference states at room temperature, right? Remember, for enthalpy, the reference states was the equilibrium state at 1 atmosphere pressure at room temperature. For the entropy, it's taken quite a bit differently, and you'll see in a second why. The reference state is actually taken at 0 Kelvin. So the reference state is the entropy of the elements in equilibrium in their equilibrium state at 0 Kelvin, at 0 degrees Kelvin. So this is where we set S equal to 0 joules per mole per Kelvin. Now, if you remember how we did compounds for the enthalpy, for the enthalpy we said, well, for compounds we measure the heat of transformation, and that's going to give us the compound energy. You could do that in principle for the entropy, but there's a simpler solution through the third law of thermodynamics, which states that as T approaches 0, and that's 0 Kelvin, the magnitude of any entropy change in a reversible process is 0. I probably should say it approaches zero since I have t says. This is also called the Nernst law. This is the same Nernst as the electrochemical Nernst. He enunciated in 1906, and he got the Nobel Prize in 1920. Planck sort of made a generalization of that in 1911. So all these famous people who did an awful lot of other stuff also did thermodynamics on the side. Why is this important? Because you can always imagine a reversible reaction to go from elements to compounds. And what that means is, since we've set these equal to zero by the definition of the reference state, the third law now tells me that this is zero too. And so the kind of maybe slightly cavalier statement here is that the entropy of everything at 0 Kelvin is zero. More precise, the entropy of everything in its equilibrium state is zero. So if a material is not in its equilibrium state at zero, which may be a little tricky to define, its entropy isn't necessarily zero. You will read slight modifications of this in books, and some of them are not quite correct, but it's out of hair splitting. Some people will say the entropy of perfect crystalline solids at 0 Kelvin is zero. And that's kind of 99.9% correct, but you know that the equilibrium state of not everything is a solid at 0 Kelvin, right? Helium, I forget always, 3 or 4, right? Is a liquid at 0 Kelvin, right? So thermodynamics really only makes a statement about the fact that it's the equilibrium state, right? And if you think about it, that should make sense, right? Pure thermodynamics never tells you anything about how a material looks inside, right? It just can tell you it's the equilibrium state. You decide what the equilibrium state is, right? So this implies that the zero temperature isotherm, so the line that connects all states at zero temperature, is actually also an isentrope. So it has the same entropy. So the 0 Kelvin isotherm is an isentrope. So a line of constant entropy. As you're going to see in a second, this is remarkably important. Pretty much anything that is problematic in the world is due to this. Well, not everything, but everything technical. But the sort of more esoteric result of this, which is the one we usually prove in thermodynamics, is that you can prove with this that it's impossible to reach 0 Kelvin. And let me walk you through an argument. So if you want to go to absolute zero, there's a few conditions you can impose on the process, right? Because absolute zero means that you're colder than anything else. So you cannot do this by heat transfer, right? So if you have a system that you want to get to absolute zero, you can't do this by extracting heat, because as the second law tells you, heat only flows from high to low temperature, and there is nothing lower than zero. So heat extraction is not an option, right? So by definition, if you want to go to lower temperature than anything else, you need to be adiabatic, right? So because your environment is always going to be warmer than yourself. So the best thing you can do is insulate yourself from the environment. So How else do you lower the temperature of something if you cannot extract heat? Well, we've seen this, right? The way you can lower the temperature of something is by extracting energy as work. If you have the system perform work, you can extract energy, and that drops the temperature. Remember, the adiabatic expansion of an ideal gas is the best example of that. So the only way to potentially cool down to absolute zero is make the system do work. Right? Because if W is negative, then delta U is negative, right? And then the temperature decreases. And 3, since we want to do this as efficient as possible, we want to do this reversible. Because if we reversible, we get the most negative W. So what does that mean? We have to be reversible, we have to do work, and we're adiabatic. That means we are at constant entropy. So the process we will have to do is isentropic, right? Because we are adiabatic, so no heat flow, and we have to be reversible. So we have to be isentropic. So let's see how we would do this. And this is actually how people do cool. So how do you make a system do work? You make a system do work in general by displacing an extensive variable, right? So you could make a system increase its volume, right? So that's changing its extensive variable volume that delivers work on the environment. But I could invent other cooling techniques, right? Magnetization is an extensive variable, right? I could do something with that and make a system do work on the environment by demagnetization. And there's actually a technique called adiabatic demagnetization, which cools systems. It's actually the way you get to very low temperature. But so in general, you want to have a displacement of some extensive variable x. And I think by now you understand that I use the word displacement in a general way, right? It's just you're changing the extensive variable. I just use it in an analogy with displacement in the differential FdR. So the problem you're going to see with that is that it doesn't quite get us where we want to be. So let me draw entropy as a function of temperature. And I'm going to draw it for two values of the extensive variable. So I'll call the first one, again, entropy has to be 0, right? So let's say this is a constant entropy line. Sorry, this is the entropy as a function of temperature at constant x0. Right, that's some value of the extensive variable. And now let me draw it as at another value of x. So maybe I'll call this x prime. So because the change of extensive variables can be done reversibly at 0, these curves have to come to the same 0 entropy here. And you'll see that's part of the problem. So how would I do cooling? So let's say that I get somewhere with a refrigerator. So somewhere is the lowest temperature I get by other means, right? This is sort of T, you know, you could call it T lowest by refrigeration. So the way in my attempt to get down to 0 Kelvin, that's the last place I can give off heat to something, right? That's what it means, right, to refrigerate. Okay, so what would I do? So I would do a change in extensive variable. So I would go from x naught to x prime. So that drops the entropy. So that means that I have to give off heat here. For example, if this were volume, this would be compression, right? If I do an isothermal compression, I would have to give off heat, right? So that's an example. Okay, so how do I lower the temperature now? Well, we defined it there, right? We have to be isentropic. So what would we do? We would insulate the system. So we would stay at constant entropy. So we have to follow an isentrope. So we would let the system expand back to the original value of x naught. So we would go this way, right? So this would be done by insulating the system because we have to be isentropic and reversible. So we end up at this temperature. But the question is, what do you do now, right? I mean, what do you do now, right? I mean, you're here, you're in the land where no heat can be extracted anymore. So what you would really want to do is step down this curve, right? What you would really want to do is repeat this process. Go down again, do this, do that, do this, do that, right? And keep on going down to zero. But the problem is you cannot deliver heat anymore here. So you cannot do this step, right? Now, you could probably imagine a system by which you try to do this, right? If I started doing this with a ton of material, like literally a ton, here, right? Then I could come to here with my ton of material, and I would now separate it, right? And I'll keep 1 kilogram that I'm going to take further down, and I let that cool against a ton of material. I would actually kind of like move slightly to the right here, but I would still come down in temperature. But the problem is because of what happens to the entropy here, you'll be able to convince yourself you can never get there. Because actually the steps you start to take here get smaller and smaller. And so it's a bit like the turtle that never crosses the finish line. So this is sort of, I hate to call it a proof, because there's a lot of arguments about it, but you could say an argument of why the third law of thermodynamics is equivalent to the statement that you cannot, that 0 Kelvin is unattainable. Note that if the third law were not true, this would be trivial, right? So if the third law were not true, then I would have different entropy values, right? This would be x naught, this would be x prime. And then all I need to do is a few steps of this, right? Bam, I'm at 0, right? I do 2 work delivery processes here and I'm at 0, I'm done. Right. So the third law is consistent with this idea that you cannot reach 0 Kelvin. You can kind of like, if you want to think hard about this at some point, which I'm not going to do because it's Friday, this is also kind of telling you something that getting to lower and lower temperature to be more and more costly. And think about this, right? Do you remember in the beginning when I showed you the different amounts of work you had to do when you took different paths to do a compression of a gas? Remember, like if you first went down in the diagram and you compressed lower, less and less work. But moving any system to lower and lower temperature is going to get more and more costly. And that's what you can infer from this. I'm not going to do the brain this weekend and make it hurt. You should think about this. Okay. Oh, let me ask you something else. Let me erase something because I need space. Since, let's say, Cp is T times ds dt, and this should be specific heat capacity, right, at constant P, right? So I'm going to rewrite this as ds is Cp over T dt, right? And again, all at constant pressure. Does that tell you something about the heat capacity near zero? Because as I get closer and closer to zero, at some point I'm starting to divide by zero here, right? So the entropy would get very large, which seems very counterintuitive, right? And so this is already telling you stuff about what the heat capacity is going to do at zero, right? The heat capacity is going to have to go to zero as well, faster than T. And I know some of you have seen that already, and we'll see that later in statistical mechanics, right? Typically, heat capacities go to zero, like the third power of T, or exponentially with T. So they will kill this divergence of 1 over T. So this is already telling you that the heat capacity cannot stay finite, which is, when you think about it, kind of weird. There is no classical argument in classical mechanics you can make that the heat capacity should go to zero at 0 Kelvin. It is only a result of quantum mechanics. So there's some weird intertwinement here of quantum mechanics and thermodynamics, because I haven't actually used anything microscopic or quantum, but we're getting here a result that is already hinting at quantum mechanics, right? Actually, you should write this down, and when we do stat mech in October, you should remind yourself, do I understand why the heat capacity has to go to zero from a microscopic perspective? Because in classical mechanics, it doesn't, right? Okay, let's do something practical though. So let's do a few entropy calculations, just to get the hang of it. And since we only know one system so far, let's do our favorite ideal gas system. So what's the entropy change in an adiabatic reversible, I could stop writing now, but expansion of an ideal gas? Okay? This is much more fun in class. Adiabatic, reversible, that means by definition that delta S is zero, right? Because it's adiabatic, so Q is zero, it's reversible, so ds is equal to del Q. Let's calculate the entropy change in an isothermal reversible expansion of an ideal gas. Okay, so let's figure out how to do that. So this is not that easy, right? Because you can't really integrate these things, right, here, because these are given at constant pressure, or the other one that I erased at constant volume. And when I do an expansion, by definition, I'm not constant pressure or constant volume in this case, right? So both pressure and volume change, so I can't just integrate Cp over T, right? So there has to be another way. There has to be. Okay. So let's draw this in a PV diagram. Right. And so we expand around an isotherm. So we know how to calculate the work. And if we know how to calculate the work, we actually know how to calculate the heat flow, right? Because delta U is del Q plus del W. And for an ideal gas, this is equal to zero for an ideal gas. So del Q is equal to minus del W. So it's equal to PdV. So that means that ds, which is del Q over T, is P dV over T. And then I can substitute in, you know, ideal gas stuff, right? P over T is NR over V. So that means that delta S, if I integrate this, is NR log V over V, right? Log V final over V initial. Okay. I can substitute pressure in if you prefer it in pressure, right? Then this is equal to minus NR log P final over P initial. Because T, it gets eliminated, right? The thing is isothermal. I'll stand here a bit since I know it takes you time to write. And maybe I can like reach over and, does that work? Can you see the board and stretch my arm? I should have an eraser on a stick, like, so I can stand there and erase there, but I think maybe the camera is going to track me then. Okay, I'm giving up. Maybe you should take screenshots. I guess you're already doing that. You're so smart. Okay. I feel like a comedian who has no audience, but maybe Jen Young, maybe you can like sort of cue up applause once in a while, or like in comedy shows or laughing. Where are you, Jen Young? No. Okay. So what about an arbitrary change of an ideal gas? So let's say I'm here and I end up here and I go through some crazy path. There we go. That's my path. How do you solve that problem? Either somebody joined late or somebody's so bored they've left. Okay, how do you solve that problem? Well, entropy is a state function. So if I want to know the difference between two states, it's path independent. So I integrate along whatever I know. So I know how to calculate it along constant pressure paths. I can calculate along constant volume paths. And I just figured out how to calculate it along isothermal paths. So I can just divide this, right? I'll do a isobar piece and then I'll do an isothermal piece. Right? So this is constant pressure and this here is isothermal. Okay, so along the isobar, what do I get, right? So ds is equal to, in this case, ds along the isobar plus ds along the isotherm. So along the isobar, I integrate Cp dt, which I just erased. So practical, ncp, this is ncp dt over t. And along the isotherm, I calculated it there, right? So that's minus r d dp over p. And since you are not undergraduates, I don't have to tell you how to integrate dt over t. So and you know, let's get rid of the n, right? Let's do this per mole. Kind of cool, right? So here's why this is cool. Remember all this work we did to calculate the adiabatic expansion of an ideal gas? When you see this, well, what's adiabatic? Adiabatic reversible expansion. Let's say I have to solve this now would be adiabatic reversible. That means that ds is equal to 0, right? That means that Cp dt over t is equal to r dp over p, and voila. that is the differential equation that leads to the adiabatic expansion, right? Because when I integrate this, I get the log of T final over T initial is the log of P final over P initial to the power R over Cp, right? Well, times R Cp, right? This leads to the equation of adiabatic expansion of an ideal gas. So you have become richer in intelligence content because now you know how the entropy behaves as a function of temperature and pressure. So you can invert that, right? That means you know how temperature has to relate to pressure to stay on an isentropic path. Okay? I think I'm confusing to you, but okay. What are we going to do now? Oh, I forgot to play the song Entropy. I was going to stick to my music, but introductions to class, there's a good song about entropy. There's actually two. One is a hard rock one, and the other one's a bit softer. I'll play it next time if I think about it. There's also a movie clip where Albert Einstein explains entropy to Marilyn Monroe. I should really try to dig that up. So, okay. The combined first and second law. So, we started by writing the first law in terms of flows. And then we figured out how to write the work in terms of variable changes of the system, right? In general, this is written as sum I yi dxi. And because I can always take a reversible path between the states I'm spanning, right? So if this du is taken between a state 1 and a state 2, it really doesn't matter what causes that differential change. I can always calculate it along the reversible path that connects the two states. So that means this has to be TdS always. So what that means is that du, the change of internal energy, is equal to TdS plus sum I yi dxi. So when you read literature that is not formally approved in this class, then you will occasionally get confused because occasionally people will say, well, this is only true for reversible, blah, blah, blah. That's not true, right? What this equation tells you is if I change a state, right? So I change S and X, right? These variables specify a state. This is my change in internal energy. That has nothing to do with reversible or irreversible, right? You're just looking at a change of state in the variable space of the system. It really doesn't matter. All these things are well defined in each state. It really doesn't matter if I did that reversible or irreversible, right? Okay, if I have a simple system, for us a simple system is one with only PDV work, then du is TdS. You know, TdS sounds almost like tedious, right? Have you ever thought about that? That entropy is tedious. Du is tedious minus PDV, right? Okay. So just for the fun, I'm going to rearrange this equation because it's Friday. So I'm going to rearrange this and put S on the other side. So I'm going to write this as, is green a good color? Más o menos, okay. I mean, I gotta say, otherwise it's pink here. I've lost my red pen. Oh, okay, black would be good, I guess, but it's so harsh. Okay, so I'm gonna rearrange this and write that ds is du divided by t minus some I yi divided by t dxi. And so for a simple system, ds is equal to du over t plus p over t dv. This high-level math leads us to some important conclusions. So it tells us that u is a function of s and the xi, right? Because that's what this mathematically says. Variations of u depend on variations of s and x, right? This is a multivariable differential, so this has to be the functional dependence. And I can say the same for entropy, that entropy has to be characterized by u and xi, right? Just by looking at the differential. So these two fellows are called the fundamental equations. But really it's only one, right? Because I could just substitute here. There's really only one fundamental equation. There's just two forms of it. And like any good piece of physics, we're going to tell you that if I knew the fundamental equation, I would know everything there is to know about a system. And then like any good physics class, I'm going to tell you, but we never will know the fundamental equation. Okay? So, but we will know pieces of it. In thermodynamics, we tend to use this one. But when we do statistical mechanics, it's actually kind of easier to do this. And we'll show you that later. It actually is easier to work with entropy differentials. And again, to run a bit ahead, you know, in statistical mechanics, they put stuff in an exponential, right? Some Boltzmann factor. This is basically the piece that goes in the Boltzmann factor. You can already recognize it, right? It's like E over T, right? That's the stuff that goes in Boltzmann factor. And this will be the kind of pieces that go in Boltzmann factors when you have more complicated systems. But anyway, you could totally forget that if you want to today. So these differentials imply important things. The implication is that intensive variables, so these are the things that are not u, s, and x, right? Intensive variables are the partial derivatives of the fundamental equations. So I can easily do that show that by taking the multivariable differential of the fundamental equation. So let me do this complex piece of math. So I'll write du as du ds at constant xi times ds plus sum over all the work terms I du dxi at constant s and the xj constant that are not equal to I times dxi. This really complex piece of math, right, which is really just writing the differential of a variable, of a function with multiple variables. This has to agree term by term with what I got from the first and second law. And now it's going to get hard because I have to run over to the other board, show you this, memorize this now, and I'm going to come back here. And this has to agree term by term with this, right? Because this has to apply to the full dimensionality of the space. So what that means is that t has to equal the first partial of u with respect to s. at constant xi. And since u is a function of all the extensive variables, that means that t is some function of all the extensive variables as well, right? And the same for the other intensive variables. yi is the u dxi at constant s xj that are not equal to I, and that would lead to a function yi as a function of s xi. Okay. These, drum roll, are called the equation state. And for a simple system, we would have the statement that T is the U ds at constant V, and P is minus du dV at constant S. So knowledge of the fundamental equation or all of the equations of state is equivalent, right? Because if I were to know all the equations of state, I could integrate them because they are the partial derivatives, and I would get back the equation of state up to a constant, right? Okay. If I only know one equation of state, like let's say I just know T, what happens when I integrate T? How much do I know about U? Remember, this is like many years ago, and you guys are all so smart, you probably took like differential calculus like super early, like in kindergarten. So you probably totally forgotten this, right? Like what happens if I just give you T as a function of S and X? Well, actually do the simple system. So I just give you T as a function of S and V. Come on, camera, come down. There we go. How much do you know about U? You only know it up to a function of volume, right? Remember, if you have a function of two variables, you know one of the partial derivatives. When I integrate that, right, I would get some knowledge about U, but I would only know it up to an unknown function of volume, right? To get that function of volume, I would need the second equation of state. This one here, sorry. Come on, camera, come down. Here we go. Okay? So I have a brain twister for you. Well, it's not that hard. How many equations of state are there in a system? How many equations of state do I need to characterize a system? Well, oh, somebody was going to say something. Go ahead, Louis.
Yeah, we need to have n work terms, n plus 1.
Say it again. I think it's right, but you know, my hearing is bad from listening to too many loud music.
No, if you have n work terms, then you have n plus 1 equations.
Yep. So it's the number of conjugate pairs. So as Louis said, it's exactly that, right? If I have n work terms, then I have n plus 1 conjugate pairs because I have the TS pair, right? And then I have n plus 1 equations of state. Okay, that wasn't a twister. So what about an ideal gas? If I believe what I just wrote down and what Lewis said, how many equations of state should there be for an ideal gas? I have one work term, so there should be two equations of state. But you know, the bad college I went to, the not so top tier college I went to, only told me PV is nRT, which is 1. So what's wrong with my math? Like, do you need to get your tuition back from undergraduate? Did they tell you something that was not right? Is there a second equation of state for an ideal gas or not? Think about it this way. If I tell you this about an ideal gas, have I told you everything? Have I told you everything there is to know about that ideal gas? The answer is no, because I haven't told you the heat capacity. Ideal gases can have different heat capacity. So I haven't told you, for example, what Cp is. And if I do it in the variable space, right, what Cp is as a function of T and V, for example. If I had that function, I could fully specify the equations of state. And you can kind of see that, right? Because if I integrate this, what am I going to get? I'm going to get S, right? Right, because Cp is related, right? It's the derivative of the entropy. And that would be my second equation of state, right? I would have to do some manipulation of variables. This one is essentially a mechanical equation of state, right? The PV one. This is the heat equation of state. You can't always cleanly separate them since the equation of state in principle relate all the variables. But in this case, you can sort of see a different source of it. Okay. So for the last time, I'm going to come back to our story of how many variables there are. And after that, well, I can't guarantee that I will never use the word variables again, but so how many variables are there really for a thermodynamic system? And really what I'm asking, how many independent ones? And remember what I said before, right? You have all the extensive variables that appear in work terms. You have all their conjugates, yi. And then you have T and S, right? Which is sort of the extra conjugate pair. So before we said if we have n work terms, I have 2 times n plus 1 variables, right? Because I have n plus 1 conjugate variables, extensive variables, and n plus 1 conjugates of them, the intensive variables. But now what I've shown you is that I also have n plus 1 equations of state. So the dimensionality of the system, the degrees of freedom is really n plus 1. So I have what this implies, right, that is I have in general n plus 1 degrees of freedom. So my independent variable space is n plus 1. And again, this makes sense, right? If I do a simple system, I have 2 conjugate work terms. No, I have 1 work term, I have 2 conjugate pairs, so I have 4 variables. But I have 2 equations of state, so I have 2 independent variables, right? That's why I really like simple systems, because I can draw them in a 2-dimensional space, right? Okay. The last thing before I let you hunt Rome free is I want to prove the Euler relation. And this is so I don't have to do it later, since it's slightly boring, but it only takes 5 minutes, so work with me here. But then I can use it later. You know, the Euler relation, if you weren't confused enough about differentials, the Euler relation is going to confuse you even more, because it says actually that U is equal to Ts plus some yi xi, which is kind of weird because before we wrote this all with differentials, and this just seems like a poor person's version of integration, right? That I'm just writing as the products. So, but turns out that this is actually true. And I'm going to prove this to you. And first I have to state that U is homogeneous of first order in its variables, which is extensive variables in the extensive variables. If you've forgotten what homogeneity means, let me just repeat it for you. So you are homogeneous of order n I think I use R in the notes, so let me use R again. If you have a function and you multiply the variables all with some constant, so the function the function of x1, x2, I multiply every variable by lambda. This is equal to lambda to the power r times the original function. So being homogeneous of order n of order 1 isn't particularly strange, right? Because it's just a statement of extensivity. We said that U is a function of S and Xi. These are all extensive variables. So by definition, they are homogeneous of order 1. Because if I multiply the system by a factor 2, because these variables are extensive, they all get multiplied by 2, and so does the internal energy. So saying that something is homogeneous of order 1 in extensive variables is just saying that they're extensive. So, but let me prove the Euler relation. So I'm going to write down the homogeneity condition. So this has to be equal to lambda U times the original function. So if you believe that, it's kind of easy to prove the Euler relation. So I'm going to take the derivative with respect to lambda here. So I'm going to take d lambda on both sides. So that means I get du d lambda s times d lambda s d lambda plus the same for all the work terms, plus some I d mu d lambda xi times d lambda xi dxi. And then if I take the right-hand side, the derivative of lambda, so that's just u s xi. This very high-level math leads us to the Euler relation, because this here, of course, is trivially s, right? And this here is trivially xi. And this here, I'm going to evaluate at, since lambda is a parameter, I'm just going to evaluate it at lambda equals 1. So then I have du ds, because this has to be true for every value of lambda. So I'm just going to use lambda equals 1. And then I have du ds here. And what is that? Du ds, this is equal to t, right? Because that's the equation of state. And this here is equal to yi. So I've just proven the Euler relation, right? I've just proven that because the left-hand side is ts plus some I yi xi is equal to u as a function of s xi. It's a bit twisted, right? So just when you thought you had all the differentials under control, I'm proving you, like I said, what looks like a really bad integration, right? But there will be some interesting consequences of this, right? If I take the differential on the left-hand side and on the right-hand side, something interesting is going to appear, right? Because if I take the differential of the product ts, I'm going to get t ds plus s dt, right? And if I take this differential, I'm going to get some yi dxi plus xi dyi. A piece of these differentials is equal to du, right? So there's some other piece that's going to have to be 0. And we'll derive that later. So that's why I'm not writing it on the board, because I want to not spoil the fun. That's what's called the Gibbs-Duhem equation, which is the coolest thing ever. But you're going to have to wait a few months for that, because we really use the Gibbs-Duhem equation when we do solution theory. So I'm done early. Any questions? Otherwise, you could have breakfast, enjoy the rest of your day, and I'll see you on Monday if I don't see you at office hours. So enjoy the rest of your day. Bye. Take care.